All right, so we're going to look at our reactions of our aldehydes and ketones. And I want to remind us that we've already seen aspects of this, like on this slide here. We do see that a nucleophile is likely to attack the backside of a carbonyl. The difference between this and a carboxylic acid or carboxylic acid derivatives is our group here is now an R group, or at least a hydrogen. And that's going to actually drastically change how this affects. Now that's mainly because the H and the R are not good leaving groups, but we do have a reactivity difference towards nucleophilic substitution. Formaldehydes are a little bit more reactive than ketones in general, and or aldehydes are more reactive than ketones in general. Formaldehyde is the most reactive of these because those H's really do not get in the way. But what will affect it on our ketones is as we get more and more substituted, or more and more hindered is probably a better way of putting that. So this having two methyls off these two locations, getting into that backside is a little more of a hindrance. So there's some steric factors that will factor into our reactivity. All right, now if we put it in the realm of all of our carboxylic acids, we see that the aldehydes and the ketones are actually more reactive towards nucleophilic substitution than the esters or the carboxylic acids. So they're almost as reactive as the anhydrides. All right, however, if we think back to the carboxylic acid derivatives, all of those, once they made that tetrahedral intermediate, they kicked off a nucleophile, and you actually did nucleophilic substitution. So it was an addition-elimination reaction. Well, we're not going to see that now because on our aldehydes and ketones, that's not really a good leaving group. So what's going to happen instead is it stays on there, and we end up protonating our tetrahedral intermediate, and it stays a tetrahedral. So this is just a nucleophilic addition reaction rather than an addition-elimination. If it is acidic enough, we can get the alcohol to be protonated and kick off, and we can get an addition-elimination product. But you have to have the right type of nucleophile here because it's got to be able to easily handle a positive charge. Now, most of them can, or many of them can, but it will actually be unique to the situation. All right, backing up a little bit. Back in the end of last semester, we talked about our Grignard reactions, and this was a type of a reaction that we dealt with. And we actually saw that this is the situation where the carbon acted like a nucleophile. Well, because carbon can act like a nucleophile, we can actually use it on our carbonyl attachment, and we can essentially make a new alcohol. Now, depending on whether this is R or H, it's either going to make a secondary or tertiary alcohol. But actually does a really good job of this. So ketones and aldehydes are definitely good candidates for Grignard reagents. Now, no matter what, we're always going to end up with an alcohol. It doesn't matter if we start with an aldehyde or ketone or even formaldehyde. You will actually get that backside attack. You're just going to essentially add whatever the R group is with our Grignard to the CO of the carbonyl and make that an alcohol. Now, something that's interesting about here's the first one here is we're making a tertiary alcohol by doing that backside attack and getting the OH off of a carbon with 3 different groups. Down here below, it's not even really what we call an aldehyde or ketone. It's actually just carbon dioxide. Well, it turns out Grignard will react with just carbon dioxide, and we will get a carboxylate group and turn it into a carboxylic acid. All right, some more examples just to see that our limitations aren't that bad here. It really doesn't matter. As long as you can make a Grignard, you can get it to attack on a carbonyl. And it will attack. There's going to be a little bit of steric hindrance on this last one, but not enough to actually stop it, so you will indeed get an alcohol out of that. Now, Grignard with esters do something slightly different. And we'll see it's always written slightly different because of this. So the first R group does indeed attack that backside. But technically what ends up happening is it does make that tetrahedral intermediate, but this gets kicked off because it's a decent leaving group. So your ester gets immediately turned into a ketone where that new R group from the Grignard is attached. So you can do it again, and you can get that a second R group on there, and then you protonate it. Mechanism of this shows what's going on. So we do get that backside attack with our Grignard just as expected, and that does form this nice little tetrahedral intermediate. But instead of actually going from there, we start first by kicking off the OCH3, and we get a ketone out of that. And then this part is the same thing we saw with a ketone reacting with a Grignard. All right, with acid chlorides, we see something similar as well, because technically that first step happens, that chlorine can kick off, and we have a ketone, and then we could have a second Grignard attack there. So same type of thing happens as with our esters. All right, and there's an example of it, and this is how we typically see it written. Rather than having two reactions and then the H3O, they just put in two equivalents of our R group with the magnesium bromide, and you put both of them onto that location where the acetyl chloride was. All right, let's do some retrosynthesis here and see if we can actually put some of this stuff together. Now, a lot of this stuff that we see on this is coming from previous material, and we are essentially building off of it, and this is definitely no exception to that. Now, we will do Grignard here, and I know that I'm doing Grignard because if I look at what I'm starting with, which is cyclohexanol, the only way to turn cyclohexanol into a methyl cyclohexene is we at least have to add a methyl. All right, so there are several ways we can add R groups on different coupling reactions. On this particular one, I'm going to turn this thing into a carboxylic acid, or into a ketone first of all. Now the reason I did that is because I can add that single methyl we add as long as I put it in with some MgBr. And then I'll follow that up with some acid. And the reason I'm doing that is because that's going to have our OH and that CH3 onto that location. And then, to turn this OH into a double bond there, I'm just going to use a pretty strong acid with some heat. Okay. All right. Well, you know what? I like doing everything we did before. So I'm going to start with that and then do NaOCl at freezing point, followed by CH3, CH2, MgBr, and some acid, and H2SO4 and heat. And if you look on the previous slide, that's likely to give us 2 carbons and the double bond. And to get rid of that double bond, and just some catalyst, so poison palladium, and that should give us that thing. All right, what is next? Oh, I'm gonna put an alcohol on there. Oh, I know what we could do. kind of go backwards compared to what we did. We're going to turn this into our Grignard. PBr3 followed by Mg and some ether, and we would have MgBr. And then I'm going to have this in there as our carbonyl. So carbonyl CH3, and to get it to turn back into a just an alcohol, I'll put an H there, because technically there is an H off this location as well. And that will do a backside attack. We'll have to do the H3O after that. And we'll put this carbon to the CH3, and then the carbonyl turns into an OH. I like that one. That one's neat. All right. Other ways we can do couplings and other ways we've introduced is with the acetylide ion, and that's where we take a terminal alkyne, treat it with a very strong base, NaNH2, make an ion out of it. Well, this ion is nucleophilic, and it will also do a backside attack and go on there. Now, on this particular one, our best bet to protonate it is with a very bulky acid. So that's why we're using this big crazy thing, because if I actually tried to do just HCl or H3 or something like that, it's going to add across my triple bond. So to keep from protonating that triple bond, we're going to use a bulky source of the acid. And we can do something kind of cool with the cyanide ion. So a cyanide ion will do a backside attack, and then protonating it will actually make an alcohol out of it. But this is actually a cyanohydrin. And there's our mechanism. It's actually quite similar to what we've seen before. So the CN does do a backside attack. And you can actually use HCN as your source of CN, since it is a weak acid. And that HCN could also be the source of the protonation. Now, if I add this to the cyanohydrin, if I add that to a basic solution, I do revert back to a ketone. Does just eliminates that cyano group. Now, we back up and look at that. That's basically saying if you take your ketone or aldehyde, treat it with your cyanide ion and a little bit of acid, you make that cyanohydrin. And yet, if you add base to it, it just undoes all that. We'll see this does actually give us a possible aid here in just a moment. That addition elimination can be quite useful, but it actually also can lead us to some interesting little products. So that cyanohydrin, having that cyanide group on there, if we treat that with HCl and H2O, that does exactly what a cyanide group would normally do and turns into a carboxylic acid. The hydroxide does not actually interfere with it whatsoever. Also, if I treat that cyanide group with hydrogen with a catalyst, I'll turn that into amine with no interference from the alcohol whatsoever. So the cyanide behaves just like a CN should, and that OH, even in that alpha position, has no effect on us. Okay, a neat one that we can do to turn aldehydes and ketones into alcohols is use sodium borohydride. Now, technically, it's a reducing agent. It's just adding H's across to both sides. And it's this little last H that ends up being added. We'll see the mechanism here in just a second. But you are essentially just adding H's here and here. It always does that right to aldehydes and ketones quite easily. Now, here is that mechanism. It's actually the BH4 part of it that does all the work. And that does just do a nucleophilic attack. The hydrogen is the nucleophile in this case. and it does make a tetrahedral arrangement, and then we just protonate that. All right, acetyl chlorides will also get reduced with BH4, but you actually need 2 of them. And it does the same type of thing as it did with our acetyl chlorides with Grignard. So the H goes on, but then we kick off that first chlorine, and then we have to have a second H to go on. So that's why there are 2 equivalents of the NaBH4. All right, now there is a different one that will reduce acetyl chlorides into aldehydes. This is a lithium aluminum tert-but oxy, 3 of those with a proton. It has to be very, very cold, but it will actually stop and only protonate 1 of those. So it'll turn acetyl chloride into an aldehyde. There is another one of these does the same type of thing. This is actually a borderline recent discovery, last 10-15 years, and that's hydrogen, but the catalyst is actually palladium treated with barium sulfate. But this is the one that we see a lot of. But the barium sulfate one can be done closer to room temperature. All right. Lithium aluminum hydride is used on our less reactive carboxylic acid derivatives. If we actually were to use it with the acid chlorides or even the aldehydes or ketones, there's a chance it could be too violent. So lithium aluminum hydride is actually stronger, but if we actually use it with esters and less reactive, we'll get reactions out of it. So lithium aluminum hydride with an ester will actually make alcohols. It's going to put this H on, and then in a second reaction a second time. So it puts it onto the aldehyde and the ketone. And that's what we're seeing in our mechanism. So it goes on, and then a second one goes on here. All right. We also have a derivative of lithium aluminum hydride, or a derivative of our reducing agent, better way to put that, that will actually stop an ester at the aldehyde level, and that is this DIBALH, which has got these isobutyl groups, 2 of them, attached to an aluminum. And most people do refer to this just as by those abbreviations. All right, lithium aluminum hydride will actually work with carboxylic acids. It does indeed turn it into just a standard old alcohol. It does something very similar, except that this time the H actually, or the aluminum, helps attack this last H, and we release it as hydrogen gas. So these 2 end up connected. That forces this to come up here, and we get a weird little carboxylate ion. Now I say weird because almost as soon as it's formed, that aluminum, the ALH3 that we had here, does get attracted to it, helps stabilize it. But that allows this whole thing to be a better leaving group. And we make an aldehyde out of that because this double bond comes in and that H was technically already out. And then once we have their aldehyde, then the aluminum hydride, the ALH4, is able to do a backside attack with that H and turn it into our alcohol. All right, so lithium aluminum hydride with amides will actually turn them into amines. It essentially turns that carbonyl into a CH2. Rather than an alcohol. And the mechanism for that will show you what's going on. We have a very similar thing that happens with our nucleophilic hydrogen here. It actually attacks this H and we kick off hydrogen gas. But this new imine type bond is formed. The aluminum, the ALH3, does actually go up there and gets with the oxygen just like before. But that now enables us to move this double bond out here, and we get an unstable tetrahedral intermediate now with 2 lone pairs and a negative charge on that nitrogen. But as that formed, this OALH2 is able to leave a heck of a lot easier, and we actually reform an imine. Very similar to this imine, but this one's going to be a lot more stable. And now we have a proton attack it from the ALH4 again. And we now have our amine with 2 H's added to the carbon that was the carbonyl. All right, so more reductions. Now we've seen these two. They are technically reductions. Anytime you add hydrogens or remove carbon-oxygen bonds, you have a reduction. So just the hydration is a reduction. Hydrogenation, totally different. Hydrogenation is a reduction. We're going to add hydrogen across the double bond or a triple bond, get rid of those pi bonds, and turn alkenes and alkynes into alkanes. And that will work on any pi system. You might have to change the catalysts, but as long as we have the right catalyst, we can be quite selective. All right, we also introduced this one ages ago. Your textbook didn't have it in the chapter where we introduced it, but it was a triple bond with a sodium, lithium, and liquid ammonia. You could actually make a trans double bond, and we do know the mechanism of that. You make a radical anion, which turns into a vinyl radical, which turns into a vinyl anion. And you end up adding H's that are as far away from each other as possible, so they always end up adding in the trans position. All right, now here's something kind of neat that we're going to introduce now. Turns out all molecules, generally speaking, when we do reactions, if they have multiple functional groups, you're going to be able to treat them selectively based on what you're adding in there. So we call it chemoselective. Like for instance, I have a reaction with 2 different carbonyls. One is a ketone, one is an ester. If I treat that with sodium borohydride, I know the only thing it's going to react with is the ketone because the ester is not strong enough to react. So this NABH4 doesn't react with just any carbonyl, it reacts with select ones. And even that sodium and lithium with ammonia, we know it won't do anything at all with a double bond. So it's very selective, it's only going to react with the triple bond. All right, but there are times when we need to be a little bit more careful. Like on this top thing, I got an aldehyde and I have an alkene, and if you look down below, I'm removing one or the other or both of those pi systems. Like over here, we want to come up with a means to just remove a alkene bond. Now, our book points out that if I just use hydrogen and I change this catalyst, just that poison palladium, I can generally leave aldehydes alone. Now the reason I'm saying generally is because if I use the wrong catalyst, like that rainy nickel for instance, I would actually add across both double bonds and get an alcohol. And in general, this is a little bit more likely even here. That poison palladium may or may not actually stop there completely, but we could always turn this back into an aldehyde with just some PCC. Now the last one's a little bit more interesting because we do have means to actually reduce just the aldehyde, and that was that sodium borohydride. Going to follow that up with a little bit of H3O plus, and we could actually react the carbonyl part and not anything else. All right, now our aldehydes and ketones with amines end up making imines. or enamines. Is what we're going to see two different names for these. But imines is just a carbon-nitrogen double bond. And technically, all that ends up happening is the nitrogen is going to replace the O. And the hydrogens that were on the nitrogen will go off with the O, and you actually end up making water. But this imine is named based on that double bond. And the mechanism generally shows what's going on. The nitrogen's lone pair will do a backside attack to the carbonyl, and then we're going to essentially protonate the oxygen to stabilize it, then deprotonate the ammonia to stabilize it. That will give us a tetrahedral intermediate, which we will then see the results of protonating the OH and turn that into a good leaving group. And when it kicks off, we actually form that imine bond, but it's a protonated imine, and we'll have to have a base come in and remove that last hydrogen to give us the imine. But do notice these are all two-way arrows. Any one of these could reverse. These are actually in equilibrium with each other in that acid solution. All right, now certain ones we do that are a little bit more favoring making the products can have other uses later on. We're not going to do much yet with our oxamines or hydrozones. That's good because hydrazine and hydroxylamine are actually both kind of dangerous to keep around. So you wouldn't necessarily want to do this and store them, but we're going to see later on there's some neat things we can do with these two derivatives. All right, now enamines are kind of like imines in the sense that if you think about this, the starting conditions are exactly the same. The problem is this doesn't have two hydrogens on it. On all the previous one, the amines were primary or just even ammonia will do it to a degree. But the secondary amines actually go on there with those two R groups, and we get our second H from an adjacent location or an alpha position to the carbonyl. And that creates an enamine, which is a double bond adjacent to the nitrogen. And this mechanism looks kind of similar. Our lone pair of the nitrogen does do a backside attack, and it does actually create this thing. We will protonate and deprotonate just like before. So these first three steps are exactly the same to get us to our tetrahedral intermediate. We are going to still see the same thing where we protonate our OH to turn it into a good leaving group. We do form the carbon-nitrogen double bond. That's the imine, and it is still protonated, or it's still positively charged, sorry. But I can't deprotonate that because there's no H's on there. So I deprotonate a neighboring location and then move the pi bond to that adjacent location. All right. We use this because it is actually going to disguise the carbonyl, because I can actually undo an imine by just adding water and acid. All right, what do I mean by that? Well, we can do some interesting things with these, like we can make amines, this technique. And we're just actually turning the O into a nitrogen on this to make the amine. This one's a little bit dangerous to do because this one's ever so slightly unstable. But as long as we do it just right as a little reactive intermediate, it will work, and we can turn a carbonyl into the location where the nitrogen's attached in the amine. All right, so where do we use these? Well, a cool thing is we know carbonyls have certain reactivity. This doesn't have the same carbonyl reactivity. So I could actually react a carbonyl with a primary or a secondary amine and make either an imine or enamine. And then by treating it with this cool stuff, I can just remove those pi bonds. And I can actually turn it into a tertiary amine or a secondary amine. All right. Next thing I want to look at is a little weird equilibrium we're going to have with our carbonyls. Turns out all carbonyls, aldehydes and ketones especially, will react with just water and make geminal diols. Geminal meaning the OHs are both coming off the same location, but it's just a hydrate of it. Now, it is an equilibrium between these two, and the mechanism is kind of what we'd expect. We're going to actually protonate our carbonyl to make this a little bit more electrophilic, so our nucleophile can attack easier, and then we just deprotonate it, and we have a very neutral tetrahedral. But everything's two-way, because I could just as easily undo all that and go backwards. The acids just needed to catalyze the reaction. And we have an interesting dilemma. Some of the time, the carbonyl, as in the aldehyde or ketone, is favored, and sometimes the diol is. And there's really not a rule that says it's one way or the other. It does have quite a bit to do with this other effects on there, the other parts of the molecule. So what I mean by that, if I have a bunch of R groups that are big bulky things like methyls, they're going to be adding some steric hindrance. So something like aldehyde would be more stable as that tetrahedral. And then something else I can do to speed that up, especially if I have bigger molecules like these phenyl rings, if I put electron withdrawing groups on there, pulling electrons away, that's going to actually make it even more convenient for a nucleophile to go in there and neutralize that withdrawing effect. All right, now something we can do to prove this is actually happening, because the weird thing is, how would you really know if it's totally reversible? Well, what we can do is we can put in some heavy water, some H2O with some oxygen 18 in there, and then later on test the sample. And what we find is if we leave it in there, we will get some of that O18 as part of our carbonyl. And that's how they're able to prove that this does actually occur. All right, that's going to lead us to something kind of neat. If I think about this particular reaction, and if I want to try to do just something simple like the lithium aluminum hydride or the sodium borohydride, I would actually get reductions, but it would be primarily to that location, because ketones are more reactive than esters. So how would I reduce an ester to an alcohol and leave that carbonyl alone? Well, we kind of alluded to what we could do already on this. So those imines we introduced, we could use that to protect it. Now, we're going to use something different because the imines actually can be stinky. And this is just ethylene glycol. That's just the active ingredient of antifreeze. So if I put that in there, I make this acetyl group. Well, this acetyl is no longer a carbonyl. And since it's no longer carbonyl, if I treat the structure with lithium aluminum hydride, it would actually turn that part into an alcohol. And then if I use acid and water, I can turn that into the alcohol rather than the O minus, and I'd actually undo the ethylene glycol part. All right, so the only thing we have to worry about is how would I know this reacts with the ketone and not the ester? Well, that's the overall reactivity. It's going to react with the more reactive carbonyl first. That's why it's called a protecting group. Protecting groups are things that we can put on there and later easily remove. But while it's on there, it stops it from doing a reaction that would be problematic. All right, so that is the trick. We protect this. There's several ways to protect it. The imines would work, but that ethylene glycol is a heck of a lot easier. And then we react the other carbonyl just like we would to reduce it, and then we remove the protection. All right, so that is a common one. About the only difference it is sometimes you see propane diol instead. But other than that, these two actually do the exact same thing. They make little acetyl ring groups, and then you can undo it by just adding water and some acid. Well, there are other protections that might be necessary. Like for instance, if I want to do a Grignard reagent with this, I could actually theoretically turn this into an MgBr and then replace it for carbonyl. However, we saw in previous chapters that Grignards can't be formed when there's an alcohol there, because the alcohol would neutralize it. So we need to protect this molecule or that Grignard reaction from the alcohol. It'd be great if we could hide the alcohol. Well, it turns out we actually can. This tert-butyl dimethyl chloride, I like the abbreviation much better, TBDMS, can be put in there. TBDMS, and this imidazole, that's just a weird solvent that we're using here. It's going to actually be where we end up dumping our H's, that H. But when I actually put this in there, it turns the alcohol into more like almost like an ether, but is actually protected. It's no longer going to react like an alcohol or an ether. And now if I put the magnesium in there with the ether, I do make a Grignard reagent, no interference from this guy at all. Treat it with the formaldehyde to get the CH2OH in there, and I still have that group on there. And then this is the weird thing. It's a butyl group, 4 of them, attached to a nitrogen. So it's a tetrabutyl ammonium fluoride, and that will remove this back and protonate the other one. And we have successfully made a Grignard reagent out of something that had an alcohol on it. All right, we can also protect carboxylic acids. Like right now, if I wanted to actually do anything with this alcohol, I'd have to worry about this being in the way. And if you notice down here, what it wants to do is actually replace it with another carboxylic acid. So somebody wants to add a carbon there and oxidize it. We could just oxidize it, but that would put a double bond here. And if you notice, we want a carbon there. So we kind of want to do almost like a Grignard type thing. Or a CN, which would actually put another carbon on there. But we can't really do that with this being an ester or a carboxylic acid. So what we're going to do is actually treat it with an alcohol, turn it into an OR group, and then do a thionyl chloride to it and turn that N location into a Cl. Had we done that to this, we would have ended up with Cl's on both sides. All right. The other thing that this does is, even though this would attack the backside of a carbonyl, it pretty much won't attack an ester. So the only thing we have to worry about the CN now doing is doing a backside attack to our chlorine. And once it's on there, we do HCl and water, which would have actually turned the ester back into a carboxylic acid. We throw in some heat, it'll turn a nitrile into a carboxylic acid as well. We can also do an acetyl type reaction with sulfur groups. So if I have a ketone or aldehyde and I treat it with a thiol, I will add the thiols as substituents to it, make thioacetyls. This is a reversible process as well, and if I do it in a chain like the diols were, I probably should use propane here rather than just ethane because of the steric hindrance. But propane dithiol is a very common one on here to make a thioacetyl. Now, where this thioacetyl really comes in handy is we actually can do something kind of cool with it. So it is a good protecting group, but also once we made it, if we just treat that directly with hydrogen and Raney nickel, it will turn it into 2 H's. So while we can return it back to a carbonyl, it is an interesting means of turning a carbonyl into an alkane. All right. Another one of these is a means of turning an aldehyde or a ketone into a carboxylic acid derivatives. Aldehydes will get turned into carboxylic acids. Ketones will get turned into esters. It's very specifically the CF3, that's not a typo, trifluoroacetic acid that's been an extra O, so it's a peroxy acid. But this peroxy acid with those fluorines in there actually basically shoves an O in there. When we have ketones, though, that are asymmetrical, we end up with 2 different ethers, or esters, sorry. The O ends up here or here, and there's not necessarily a good rule that says this is the way it goes always. So it's probably safe to say mixtures. It might even be perfectly 50-50, but it's generally going to be one slightly favored over the other. So mixtures is the best way to point out. All right, mechanism will show what's going on here. So the O does do a backside attack. But since this part of it is a decent leaving group, we actually see the R, one of the R's, moves down there easily. All right. Next one we look at is just a type of reaction where we can turn that carbonyl of an aldehyde or a ketone into the carbon, making up a double bond. Now this is called the Wittig reaction, and we're using a phosphonium ylide as the reagent. So it's a phosphorus with 3 phenyl groups attached that's double bonded to a carbon with CH3 and an H. So it's a phosphorus with 5 bonds. But the neat thing is this thing behaves almost like this is positive and this is negative. So it actually is a situation where that carbon controls those electrons on one of those bonds. All right, reason that's important is this nucleophilic carbon ends up doing an attack. And we have a kind of a mechanism. It's not really a backside attack, it's more like a top-down attack. So think about this, it looks like left to right. This is more of coming down right on top of this flat molecule. But it forms this square where a nice little concerted reaction happens where the bonds move around. All right, there are some issues though. If I actually knew I wanted to make this, I have 2 potential starting ingredients. I could either have the left side with our carbonyl, or the right side is the carbonyl, and then the other side is the phosphonium. Now there is generally a nice little rule. We'd like to have the phosphonium with more hydrogens on it. All right, now this does give us some benefits. So my first 2 examples up here are reactions we've seen before. So if I were to treat this with an OH, I know it's not going to do substitution because this is tertiary, so it's going to be doing an elimination. It's either going to eliminate out here or out here. With this, definitely is a major product. All right, if I move the halogen out to that bromine and then do OH, I could get elimination, but I'm going to favor substitution. Now we know SN2 versus E2, we can use heat to get it to favor the elimination, but there's no really good way to guarantee we'd only get this. Even with a bulky base, we're still going to get some substitution products because that's primary. Although Wittig gives me only a product. So if I start with cyclohexanone and put just a CH2 off of my Wittig, I would definitely get this as my only product, no mixtures at all. All right, next little weird thing we have to deal with is conjugated carbonyls. Now, conjugated really does mean double, single, double. The pi bond would be alpha and beta to your carbonyl. All right, now we have 2 electrophilic sites if that happens. We have the electrophilic site that's the back of the carbonyl that we've seen a lot of, but this could also resonate up there and we could have this be an electrophilic site. Now, if we think back to when we first introduced conjugated system, this is almost like a 1,4 site and a 1,2 site. And you'll see it referred to that in some cases, 1,4 and 1,2. But what we're going to do to try to distinguish this from what we did back with our butadienes, where we introduced this type of thing, we're going to call this a direct site, and we're going to call this one conjugated. So conjugated and direct. All right, so if I have a standard nucleophile go in there, I would get that direct site, nucleophile, so very much what we've seen before, and I'd possibly get conjugated. And the weird thing about the conjugated, even though it's kind of drawn like this, where the double bond is definitely there, and the O- is there, it turns out we can resonate back and forth. This is a keto-enol tautomerization, and tautomerization always favors the keto form. So more than likely that H is going to come over here, and we're going to have a carbonyl back. All right, now we can kind of control this. As long as we start with the right type of nucleophile, we can make much more nice predictions. So if I have a weakly basic nucleophile, direct addition becomes a reversible process, because basically this can just get kicked right back off. But the direct addition, because it will go on and then do that keto-enol tautomerization, is a one-way arrow, because the only way for this to come off is to reform this double bond, and if the H is there, it's not reversible. So if I do have a weakly basic nucleophile, I end up almost with nothing but conjugated addition, because once it gets there, it's going to stay there. All right, now weak bases are a little bit more common. These are also weakly nucleophilic, but almost all of them we're going to get a conjugated addition, where it's 1, 2, 3, 4 away, 1, 2, 3, 4 away. So, and that happens anytime it's what we consider weak base or weak nucleophile. All right, the kinetic one is going to be favored by a strong base, or the direct addition. So if it's a strong base, it basically just drives the nucleophile is what drives the reaction, and it goes to the strongest electrophile, which is the pi bond. There is a bit of a weirdness, though. That backside can be hindered based on R groups. So a strong nucleophile, or a strong base, like the NABH4 happens to be, if I have an aldehyde, I do indeed favor the aldehyde side, and we make alcohols. On ketones, it's not nearly as good. We do get some of that, but we also get some where it comes in over here. So we end up with both. Grignard is considered a strong base, and we do end up seeing both in that case. So I got two different little structures. This one being aldehyde, we would typically expect to have more direct addition, bulkiness. So in this case, I would expect more conjugated addition. And if I change this to Gilman rather than Grignard, Grignard typically does favor, well, Grignard does give us more of a direct addition. Gilman almost always gives you conjugated. Okay, now our carboxylic acid derivatives, like chlorines and NaCl's, can do something kind of different. So the more reactive the acid derivative is, the more likely it's going to actually just do an addition, elimination, nucleophilic switch. So this isn't even going to get a chance to react with the backside. But if I have a weakly if I have a weak nucleophilic addition carbonyl, like an amide, I'm actually going to see this go over here instead. So suddenly the conjugated product is about it. So the reactivity of the carbonyl really does drastically affect how this happens. And that gets us done with this chapter. Now, quite a few example problems, quite a few things to practice, and let me know if you have any questions.